Hi, welcome back. This is the final video to the video series for today's lectures. In this section, or in this video, we're going to be covering the section Geometric Transformations. This is on page 118 of your textbook, page 118. And a lot of what I'm going to be discussing in this particular video, I'm not going to explain why it's true. I'm just going to tell you that it is true. The textbook doesn't really give very good explanation for why. Well, it actually doesn't give an explanation at all for why these things are true. And this is because the explanations are beyond the scope of this level of mathematics. We'd have to get into some deeper material, and so you just gotta trust it. You just gotta trust what I write. But if you take these facts to be true, then by using the techniques we've learned earlier in today's lecture, we can get a lot of results. Okay, so in your textbook on page 118, we have this matrix. 0, 0, 0, 1, 1, 1, and 1, 0. So what does this correspond to geometrically? Well, geometrically, if I draw my x and y axes, these points correspond to the following. So 0, 0, so this is my x coordinate, and this is my y coordinate. Okay, so x, y. Okay, so those are four different colors because they four different colors because it corresponds to four different points. So 0, 0, that's going to be here, right? Not too difficult, right? X equals 0, y equals 0. 0, 1, this is going to correspond to the point when x equals 0, right? So I go to the 0 spot, and then I go up 1, okay? So 0, 1, 0, 0. Okay, what about 1, 1? 1, 1, that's going to be 1 over 1 up. So that's right here, right? 1, 1. And then 1, 0, that's going to be down here, 1, 0. Now, if you say that, well, let me just say, it may not be, and this is what I mean by beyond the scope of the course. You might ask yourself, why? Why do these points here correspond to this matrix? Seems like, well, yeah, you can see that I can do that, right? You can see that I can write 0, 0, and then it goes down here. But you might ask, why is this natural? How does it make sense? Maybe you would have thought that you should write the matrix, say, like this. 0, 0, 0, 1, 1, 1, 1, 0, right? That's another thing you could have done. Or who knows what else you could have come up with. But I'm just going to say, look, that is beyond the scope of this course. So we're going to take this as given. Now, once we have these 4 points, if we say that these matrices correspond to geometric objects, right, then what sort of object is this? This is a square. You have 4 points, and we're gonna have the following rule or understanding that anytime you have a matrix, right, if I give it a collection of points, then I also get for free all the points in between them. Okay, so what sort of geometric object is it? Well, it's those 4 points plus the 4 lines that connect them, right? And that's a square. Not too terribly difficult. The next thing your textbook discusses is a rotation. Okay, So if you have r equals cosine theta, cosine theta, and sine theta, and negative sine theta. Okay, this is the sort of operation that takes a point and rotates it by theta degrees. So in order for us to do this, we have to use what's called radians. Okay, so if you're not familiar with that, don't freak out. It's okay. You don't have to memorize it, but it will make things a little simpler in discussing these concepts. So for example, if I have a point right here and I want to rotate it, right? I want to take it and I want to rotate it by, say, 90 degrees. Okay. Rather than saying, so that it goes here, rather than saying rotate by 90 degrees, I say rotate by pi over 2 radians. Okay? Pi over 2 radians. Okay, well, how would I do that? Well, if I had a matrix that corresponds to this point, then if I multiply it by this matrix, where theta equals pi over 2, this will give me a new vector, or new matrix, corresponding to that point. Okay, so this would be pi over 2, right? I said pi over 2, pi over 2, pi over 2, pi over 2. Okay, so great. So many of you don't know your unit circle, and that's okay. You can use a calculator to figure out what each of these entries is, but let me just say, pi over 2 on a unit circle corresponds to this point here. And so cosine of pi over 2 corresponds to the x component of that point, which is 0, because there's 0 there. And so this would be 0, and sine of pi over 2 is 1, because sine of the sign of that number gives us the y component, okay? And the y component of this position pi over 2, which is on the circle, so this is 0, pi over 2, pi, 3 pi over 2, 2 pi. The y component here is 1, so this will be 1, this will be negative 1, and 0. Okay, so you might say, what the heck? This makes no sense. All I have to say to that is, if you understood it, great, and if you didn't understand it, you can use your calculator, and you can take cosine of pi over 2, and you'll get 0. Sine of pi over 2 is 1. Negative sine of pi over 2 is negative 1, and cosine of pi over 2, again, is 0. So this is a rotation by pi over 2. So we could write rotation by pi over 2. Or you could even write r subscript pi over 2. Okay, and in general, we write r theta, where instead of pi over 2, we have theta. Okay, so how does this work? Like, why is this useful, right? So earlier in this video, I said that geometric objects correspond to matrices, and if I have a matrix T and I multiply it by that matrix R, theta. Okay, this is going to take my matrix here, which corresponds to an object, and it's going to rotate the whole thing by theta. So let's do a very simple example. So remember, if theta equals pi over 2, we get 0, 1, negative 1, 0. Now, suppose I had this point down here, right? Well, what sort of object is that? Well, it's a single point, so the geometric object would have to be a 1 by 2 vector, right? And its x components go here, and its y components go here, and its x component is 1, and its y component is 0. So let's say I want to rotate it by 90 degrees. Rotating it by 90 degrees means that I multiply it by r theta, where theta equals pi over 2. So this matrix here is what I just erased, which is, okay, so I'm rotating it by pi over 2. So cosine pi over 2, sine pi over 2, negative sine of pi over 2, and cosine pi over 2. Okay, so that's what I'm doing. And I've already simplified it when I write it right here. Okay, great. So before I calculate this, let's just think, does this make sense? Okay, so this is a 1 by 2 matrix, right? 1 row, 2 columns, 1, 2. This is a 2 by 2 matrix, and so because the inside entries are the same, 2 and 2, this does make sense. And what is the new dimension? It's 1, 2, right? So 1, 2. And of course, this is exactly what we would like, because if you have a single point and you spin it, it's still going to be a single point. And if it had an x component and a y component previously, then again, it should have one x and one y. So let's figure out what this is going to become. 1 times 0 is 0. 0 plus 0 times negative 1, that's 0. So this will be 0. And 1 times 1 is 1. Plus 0 times 0 is 0. So that's 1. Well, hey, that's actually exactly what we wanted, okay? Because if I start off with x component 1, y component 0, right? If I rotate by 90 degrees, which is what this is, I'm going to take that and I'm going to put it here, right? What is this? Well, this has 0, 1 coordinate, which is exactly what I have here. Okay, now your textbook doesn't do this very simple example. It does not do it. Instead, it does this. It does the square that we worked with earlier. So they use S, right, which is 0, 0, 0, 1, 1, 1, 1, 0, okay? And they don't use this matrix because they let theta equal pi over 3. When theta equals pi over 3, the picture is more complicated, okay? Because you're rotating by pi over 3 degrees, and that's, let's be frank, it's a lot more confusing, okay? So the point here I'm trying to make is that if we start off with these 4 points, right? If I rotate this by 90 degrees, this point is going to go here, this point is going to go here, this point is going to stay, and this point is going to go like this, right? So we should get this, right? If that wasn't clear, you know, I can show you by an example. So take this, right? Rotate it by 90 degrees, right? Like that, right? So this point stays where it is, right? This point is going up here, right? This point here is going right here, and this point here is going right here. Okay, so that's what's up. So if I do the calculation, right, just by looking at this, right, 0, 0, that should go to 0, 0. 0, 1, which is this point here, I said it's going to go down here, right? So what should that be? Well, that should be negative 1, 0, right? What does 1, 1 go to? Well, that's right here. And I said, you know, if I just rotate it, that's going to this point. Well, what is that? That's negative 1, 1. So that's going to be negative 1, 1. And 1, 0, that's right here. That's going to go up here. So that's sorry, I am confused. I guess I wrote something wrong. Give me a second. My third point here, yeah, negative 1, 1. So negative 1, 1. And my final point, 1, 0, it's going to go up to here. So 0, 1. So let's just check that actually this is what happens. Okay, so I just told you that if I rotate by 90 degrees, those 4 points should go to these 4 points, right? They should, but let's just make sure that in fact they do. Let's do the matrix algebra. Okay, 0 times 0 plus 0 times negative 1. That's 0. Good. 0 times 1 is 0 plus 0 times 0. That's 0. Okay, so far, so good. Okay, check. Okay, second entry. 0, 0, 0 times 0 is 0 plus 1 times negative 1. Negative 1. 0 times 1 plus 1 times 0. That's 0. Okay? So far, the algebra is working. Finally, 1 times 0 is 0. 1 times negative 1 is negative 1. Right? Because 1 times 0 is 0 plus negative 1 is negative 1. 1 times 1 is 1 plus 1 times 0 is, well, 1 plus 0 is 1. And for the final one, 1 times 0 is 0 plus 0 times negative 1 is 0. 1 times 1 plus 0 times 0, that's 1. Okay, so basically what I've shown here is that if I have 4 points, I can either, if I have a rotation by 90 degrees, I can follow the points and get the new figure, or I can use the matrix to send those points across. Okay, so your book is going to use a different example, so it's going to use theta equals pi over 3. And then instead of getting 0, 1, negative 1, 0, they get 1/2 square root of 3 over 2, negative square root of 3 over 2, and 1/2. Obviously, those numbers are a lot more difficult, so I did not want to do it. But hey, you have your textbook, you have this video, you have more examples now. Okay? And also, I think it's more difficult to visualize a rotation by theta equals pi over 3. Okay, that's my opinion. Finally, at the bottom of page 119, they have example 3.11. So 3.11, they use a 3 by 2 matrix. Their 3 by 2 matrix is the following. So it's P equals 0, 1, 3/4 and 4/3 and 1/0. Okay, but they don't use 3/4. They use 0.75, and they don't use 4/3. They use 1.25. Okay, good. So what does all of this mean? Well, this is just the triangle, right? Because there's 3 points. This is x and this is y. So x is 0, y equals 1. That's this point. 0.75, if this is, let's say this is 1, and let's say this is 1. Okay, so 0, 1, that's here. Okay, 1, 0, that's down here, and 0.75, that's right here, and then 125. So that's this shape. Okay, and that's exactly what your textbook has. You see? Right here. Right? Same thing. Okay, and then they rotate it by pi over 6. So in general, here's the thing you got to do. You take your shape, okay, so shape, matrix, times rotation, matrix, okay, and the multiplication is going to occur on the right, okay. Then the new matrix is going to be the rotated shape matrix. Okay, so that's the takeaway I want you to understand. If you have a shape matrix times a rotation matrix, you're going to get the rotated shape matrix. Okay, so this will conclude this section of the series. In the next lecture, we will cover Hill's system. So go ahead and read up on section 3.3, and y'all have a lovely weekend. Take care. Wash your hands and stay indoors, please.